Second Series, December 1926, Volume 28, Number 6. The Physical Review. An Undulatory Theory of the Mechanics of Atoms and Molecules. By E. Schrodinger. Abstract. The paper gives an account of the author's work on a new form of quantum theory. Section 1. The Hamiltonian analogy between mechanics and optics. Section 2. The analogy is to be extended to include real, physical, or undulatory mechanics instead of mere geometrical mechanics. Section 3. The significance of wavelength, macromechanical and micromechanical problems. Section 4. The wave equation and its application to the hydrogen atom. Section 5. The intrinsic reason for the appearance of discrete characteristic frequencies. Section 6. Other problems, intensity of emitted light. Section 7. The wave equation derived from a Hamiltonian variation principle, generalization to an arbitrary conservative system. Section 8. The wave function physically means and determines a continuous distribution of electricity in space, the fluctuations of which determine the radiation by the laws of ordinary electrodynamics. Section 9. Non-conservative systems, theory of dispersion and scattering, and of the transitions between the stationary states. Section 10. The question of relativity and the action of a magnetic field. Incompleteness of that part of the theory. 1. The theory which is reported in the following pages is based on the very interesting and fundamental researches of L. de Broglie on what he called phase waves, ondes de phase, and thought to be associated with the motion of material points, especially with the motion of an electron or proton. The point of view taken here, which was first published in a series of German papers, is rather that material points consist of, or are nothing but, wave systems. This extreme conception may be wrong. Indeed, it does not offer as yet the slightest explanation of why only such wave systems seem to be realized in nature as correspond to mass points of definite mass and charge. On the other hand, the opposite point of view, which neglects altogether the waves discovered by L. de Broglie and treats only the motion of material points, has led to such grave difficulties in the theory of atomic mechanics. 1. L. de Broglie and de Physique 3, 22, 1925. 2. A. Schrodinger and Physik 79, 361, 489, 734, 80, 437, 81, 109, 1926. Die Naturwissenschaften 14, 664. 1050. E. Schrodinger. And this after century-long development and refinement, that it seems not only not dangerous, but even desirable, for a time at least, to lay an exaggerated stress on its counterpart. In doing this, we must of course realize that a thorough correlation of all features of physical phenomena can probably be afforded only by a harmonic union of these two extremes. The chief advantages of the present wave theory are the following. A. The laws of motion and the quantum conditions are deduced simultaneously from one simple Hamiltonian principle. B. The discrepancy hitherto existing in quantum theory between the frequency of motion and the frequency of emission disappears insofar as the latter frequencies coincide with the differences of the former. A definite localization of the electric charge in space and time can be associated with the wave system, and this, with the aid of ordinary electrodynamics, accounts for the frequencies, intensities, and polarizations of the emitted light, and makes superfluous all sorts of correspondence and selection principles. C. It seems possible by the new theory to pursue in all detail the so-called transitions, which up to date have been wholly mysterious. D. There are several instances of disagreement between the new theory and the older one as to the particular values of the energy or frequency levels. In these cases, it is the new theory that is better supported by experiment. To explain the main lines of thought, we'll take as an example of a mechanical system a material point, mass m, moving in a conservative field of force, v, x, y, z. All the following treatment may very easily be extended to the motion of the image point, picturing the motion of a wholly arbitrary conservative system in its configuration space, G space, not PG space. We shall effect this generalization in a somewhat different manner in Section 7. Using the usual notations, the kinetic energy, T, is T equals 1/2 m dx over dt squared plus dy over dt squared plus dz over dt squared equals 1/2 m p squared plus pw squared plus ph squared. 1. The well-known Hamiltonian function of action w equals t minus v dt. 2. Taken as a function of the upper limit, t, and of the final values of the coordinates, x, y, z, satisfies the Hamiltonian partial differential equation. AW over dt plus 1/2 m times dw over dx squared plus dw over dy squared plus dw over dz squared plus v, x, y, z equals 0. Undulatory dynamics 1051. To solve this equation, we put as usual E being an integration constant, viz. The total energy, and S a function of x, y, z only. EQ3 may then be written grad W equals 2m E minus v squared. 5. In this form, it lends itself to a very simple geometrical interpretation. Assume phi constant for the moment. Any function w of space alone can be described by giving geometrically the system of surfaces on which w is constant, and by writing down on each one of these surfaces the constant value, say w, which the function w takes on it. On the other hand, we can easily construct a solution of EQ5, starting from an arbitrary surface and an arbitrarily chosen value, ρ, which we ascribe to it. For after having chosen starting surface and starting value, and after, still arbitrarily, having designated OZ of its two sides, or shores, as the positive one, we simply have to extend the normal at every point of the chosen surface to the length, say, dn equals dw over 2m E minus v squared. The totality of points arrived at in this way will fill a surface to which we obviously have to ascribe the value w plus dw. The continuation of this procedure will supply us the whole system of surfaces and values of constants belonging to them, i.e., the whole distribution in space of the function w, at first for phi constant. Now, let the time vary. EQ4 shows that the system of surfaces will not vary, but that the values of the constants will travel along the normals from surface to surface with a certain speed w, given by u equals E over 2m E minus v squared. 6. The velocity w is a function of the energy constant z, and, besides, since it contains v of x, y, z, is a function of the coordinates. Instead of thinking of the surfaces as fixed in space and letting the values of the constants wander from surface to surface, we may equally well think of a certain numerical value of w as attached to a certain individual surface and let the surfaces wander in such a way that each of them continually takes the place and exact form of the following one. Then, the quantity 1 given by EQ6 will denote the normal velocity of any surface at any one of its points. Adopting this view, we arrive at a picture which exactly coincides with the propagation of a stationary wave system in an optically non-homogeneous but isotropic. 1052. E. Schrodinger. W being proportional to the phase and u being the phase velocity. The index of refraction would have to be taken proportional to u dash. The above-mentioned construction of normals, dx, is obviously equivalent to Huygens principle. The orthogonal curves of our system of W surfaces form a system of rays in our optical picture. They are possible orbits of the material point in the mechanical problem. Indeed, it is well known that P equals ME equals del of W by del X, 7, with two analogous equations for Y and Z. It may be useful to remark that the phase velocity u is not the velocity of the material point. The latter is, by 7 and 5, y equals 245232, b equals 1/2 square root of 2e minus v over m, 8. Comparing 6 and 8, we see that u and v vary even inversely to each other. The well-known mechanical principle due to and named after Hamilton can very easily be shown to correspond to the equally well-known optical principle of Fermat. 2. Nothing of what has hitherto been said is in any way new. All this was very much better known to Hamilton himself than it is in our day to a good many physicists. Indeed, the theory of the propagation of light in a non-homogeneous medium, which Hamilton had developed about 10 years earlier, became, by the striking analogy which occurred to him, the starting point for his famous theories in pure mechanics. Notwithstanding the great popularity reached by the latter, the way which had led to them was nearly forgotten. Stress must now be laid on the fact that though, in our above-stated reasoning, such conceptions as wave surfaces, Huygens principle, Fermat's principle come into play, nevertheless, the whole established analogy deals rather with geometrical optics than with real physical or undulatory optics. Indeed, the chief and fundamental mechanical conception is that of the path or orbit of the material particle, and it corresponds to the conception of rays in the optical analogy. Now the conception of rays is thoroughly well defined only in pure abstract geometrical optics. It loses nearly all significance in real physical optics as soon as the dimensions of the beam or of material obstacles in its path become comparable with the wavelength. And even when this is not the case, the notion of rays is, in +C, F. Klein, Jarisberg.Dech.Math.Ver. 1, 1891, Zeitz for Mott U. Phys. 46, 1801, Guess Alba, II, 601, 603, E. T. Whittaker, Analytical Dynamics, Chapter 11, A. Sommerfeld, Atembau, German ed., p. 803. The analogy has been rediscovered in relativistic mechanics in the paper of L. de Broglie, quoted above. Undulatory dynamics. 105 physical optics, merely an approximate one. It is wholly incapable of being applied to the fine structure of real optical phenomena, i.e., to the phenomena of diffraction. Even in extending geometrical optics somewhat by adding the notion of Huygens principle, in the simple form used above, one is not able to account for the most simple phenomena of diffraction, without adding some further very strange rules concerning the circumstances under which Huygens' envelope surface is or is not physically significant. I mean the construction of Fresnel zones. These rules would be wholly incomprehensible to one versed in geometrical optics alone. Furthermore, it may be observed that the notions which are fundamental to real physical optics, i.e., the wavefunction itself, W is merely the phase, the equation of wave propagation, the wavelength and frequency of the waves, do not enter at all into the above stated analogy. The phase velocity, v, does enter, but we have seen that it is not very intimately connected with the mechanical velocity, v. At first sight, it does not seem at all tempting to work out in detail the Hamiltonian analogy, as in real undulatory optics. By giving the wavelength a proper well-defined meaning, the well-defined meaning of rays is lost at least in some cases. And by this the analogy would seem to be weakened, or even to be wholly destroyed for those cases in which the dimensions of the mechanical orbits, or their radii of curvature, become comparable with the wavelength. To save the analogy, it would seem arte necessitary to attribute an exceedingly small value to the wavelength, small, in comparison with all dimensions that may ever become of any interest in the mechanical problem. But then again, the working out of an undulatory picture would seem superfluous, for geometrical optics is the real limiting case of undulatory optics for vanishing wavelength. Now, compare with these considerations the very striking fact, of which we have today irrefutable knowledge, that ordinary mechanics is really not applicable to mechanical systems of very small, viz., of atomic dimensions. Taking into account this fact, which impresses its stamp upon all modern physical reasoning, is one not greatly tempted to investigate whether the non-applicability of ordinary mechanics to micromechanical problems is perhaps of exactly the same kind as the non-applicability of geometrical optics to the phenomena of diffraction, and may perhaps be overcome in an exactly similar way? The conception is, the Hamiltonian analogy has really to be worked out towards undulatory optics, and a definite size is to be at 1054 E. Schrodinger, tributed to the wavelength in every special case. This quantity has a real meaning for the mechanical problem, viz., that ordinary mechanics with its conception of a moving point and its linear path, or more generally, of an image point moving in the coordinate space, is only approximately applicable so long as they supply a path which is, and whose radii of curvature are large in comparison with the wavelength. If this is not the case, it is a phenomenon of wave propagation that has to be studied. In the simple case of one material point moving in an external field of force, the wave phenomenon may be thought of as taking place in the ordinary three-dimensional space. In the case of a more general mechanical system, it will primarily be located in the coordinate space, G space, not PG space, and will have to be projected somehow into ordinary space. At any rate, the equations of ordinary mechanics will be of no more use for the study of these micromechanical wave phenomena than the rules of geometrical optics are for the study of diffraction phenomena. Well-known methods of wave theory, somewhat generalized, lend themselves readily. The conceptions, roughly sketched, in the preceding are fully justified by the success which has attended their development. 3. Let us return to the system of W surfaces dealt with in Section 1, and let us associate with them the idea of stationary sinusoidal waves whose phase is given by the quantity W, equa 4. The wave function, say y, will be of the form y equals a x, y, 2 sine W over k, equals a x, y, 2 sine negative ei over k plus s of x, y, 2 over k. 9. A being an amplitude function, the constant k must be introduced and must have the physical dimension of action, energy x time, since the argument of a sine must always be a pure number. Now, since the frequency of the wave, 9, is obviously v equals b over e, k, one cannot resist the temptation of supposing k to be a universal constant, independent of z and independent of the nature of the mechanical system, because if this be done, and k be given the value h over 2 pi, then the frequency y will be given by v equals e over h. 11. H being Planck's constant. Thus, the well-known universal relation between energy and frequency is arrived at in a rather simple and unforced way. Undulatory dynamics, 1055. In ordinary mechanics, the absolute value of the energy has no definite meaning, only energy differences have. This difficulty can be met, and a zero level of energy can be defined in an entirely satisfactory way by using relativistic mechanics and the conception of equivalence of mass and energy. But it is unnecessary to dwell on this subject here. While the frequency v of our waves by EQ 10 or 11 is indeed dependent on the zero level of energy, their wavelength is not. And after what has been said above, it is the wavelength that is of greatest interest. The comparison of this quantity with the dimensions of the path or orbit of the material particle, calculated according to ordinary mechanics, will tell us whether the latter calculation is or is not of physical significance, whether the methods of ordinary mechanics are approximately applicable to the special problem or not. The wavelength A by 11 and 6 is n equals n by v equals h by 2m e minus v, 12. Here, E minus V is the kinetic energy mv squared, which indeed is independent of the zero level of the total energy. Inserting its value, we have N equals h by mv, 13. To test the question whether an electron moving in a Keplerian orbit of atomic dimensions may, following our hypotheses, still be dealt with by ordinary mechanics, let A be a length of atomic dimensions, and compare N with A. Therefore, N equals h by mva, 14. The denominator on the right is certainly of the order of magnitude of the moment of momentum of the electron, and the latter is well known to be of the order of magnitude of Planck's constant for a Keplerian orbit of atomic dimensions. So, A by A becomes of the order of unity, and, following our conceptions, ordinary mechanics will be no more applicable to such an orbit than geometric optics is to the diffraction of light by a disk of diameter equal to the wavelength. Were a physicist to try to understand the latter phenomenon by the conception of rays with which he is acquainted from macroscopic geometric optics, he would meet with most serious difficulties and apparent contradictions. The rays, streamlines of the flow of energy, would no longer be rectilinear and would influence one another in a most curious way, in full contradiction with the most fundamental laws of geometric optics. In the same way, the conception of orbits of material points seems to be inapplicable to orbits of atomic dimensions. It is very satisfying that the limit of applicability of ordinary mechanics is by equating K, essentially, 105e, Schrodinger, to Planck's constant, equation 11, determined to an order of magnitude, which is exactly the one to be postulated if the new conception is to help us in our quantum difficulties. We may add that by equation 13, for a Keplerian electronic orbit of the order of magnitude of a high quantum orbit, the relation of wavelength to orbital dimensions becomes of the order of magnitude of the reciprocal of the quantum number. Hence, ordinary mechanics will offer a better and better approximation in the limit of increasing quantum number, or orbital dimensions, and this is just what is to be expected from any reasonable theory. By the fundamental equation y equals e over h, equation 11, the phase velocity x, given by equation 6, proves to be dependent on the frequency v. Therefore, equation 6 is an equation of dispersion. By this, a very interesting light is thrown on the relation of the two velocities. 1. Velocity v of the moving particle, equation 8. 2. Phase velocity u, equation 6. V is easily proved to be exactly the so-called group velocity belonging to the dispersion formula. By using this interesting result, it is possible to form an idea how ordinary mechanics is capable of giving an approximate description of our wave motion. By superposing waves of frequencies in a small interval, v plus dv, it is possible to construct a, quote, parcel of waves, the dimensions of which are in all directions rather small, though they must be rather large in comparison to the wavelength. Now it can be proved that the motion of, let us say, the center of gravity of such a parcel will, by the laws of wave propagation, follow exactly the same orbit as the material point would by the laws of ordinary mechanics. This equivalence is always maintained, even if the dimensions of the orbit are not large in comparison with the wavelength. But in the latter case, it will have no significance, the wave parcel being spread out in all directions far over the range of the orbit. On the contrary, if the dimensions of the orbit are comparatively large, the motion of the wave parcel as a whole may afford a sufficient idea of what really happens, if we are not interested in its intrinsic constitution. As stated above, this motion as a whole is governed by the laws of ordinary mechanics. 4. We shall not dwell on this question further, but proceed to the far more interesting applications of the theory to micromechanical problems. As stated above, the wave phenomena must in this case be studied in detail. This can only be done by using an, quote, equation of wave propagation, unquote. Which one is this to be? In the case of a single material point moving in an external field of force, the simplest way is to try to use the ordinary wave equation. 5. This important theorem is due to L. de Broglie, LC. The relation is VU equals dP over dV over x. Undulatory dynamics. 1057, and to insert 4, the quantity given by EQ6, which depends on the space coordinates through the potential energy V and on the frequency EH. The latter dependence restricts the use of 15 to such functions y as depend on the time only through the factor ET over TF, A similar. Restriction is always imposed on the wave equation as soon as we have dispersion. So we shall have y equals -4r squared EY over h. Inserting this and EQ6 in EQ15, we get y plus 8nr squared me minus vp over h equals 0, 16, where y may be assumed to depend on x, y, z only. We omit changing the notation of the dependent variable, which we really ought to do. Now, what are we to do with EQ16? At first sight, this equation seems to offer ill means of solving atomic problems, e.g., of defining discrete energy levels in the hydrogen atom. Being a partial differential equation, it offers a vast multitude of solutions, a multitude of even a higher transcendent order of magnitude than the system of solutions of the ordinary differential equations of ordinary mechanics. But the deficiency of the latter in atomic problems consisted, as is well known, by no means in that they supplied too small a number of possible orbits, but quite on the contrary, much too many. To select a discrete number of them as the real or stationary ones is, according to the view hitherto adopted, the task of the quantum conditions. Our wave equation, 16, by augmenting the possibilities indefinitely instead of restricting them, seems to lead us from bad to worse. Happily, because of the very interesting character which EQ16 takes in actual atomic problems, this fear proves to be erroneous. Putting, for instance, V equals -e squared r, 17, E, electronic charge, r equals x squared plus y squared plus z squared, 1/2. We get for the simplified hydrogen atom, or one-body problem, V plus 8p E plus E squared over R, y over h equals 0, 18. Now, this equation for a great part of the possible values of the energy, or frequency constant E, proves to offer no solution at all which is continuous, finite, and single-valued throughout the whole space. For the E values in question, every solution y that satisfies the two other conditions, viz., continuity and single-valuedness, grows beyond all. In Schrodinger, limits either in approaching infinity or in approaching the origin of coordinates. The only E values for which this is not the case, i.e., for which solutions exist that are continuous, finite, and single-valued throughout the whole space, are the following ones. 1. E is greater than 0. 2. E equals minus 2nz met over h squared, nu equals 1, 2, 3, 4. 19. The first set corresponds to the hyperbolic orbits in ordinary mechanics. It is the general view that according to ordinary quantum theory, the hyperbolic orbits are not submitted to quantization. In our treatment, this turns out quite spontaneously from the fact that every positive value of E leads to finite solutions. The second set corresponds exactly to Bohr's stationary energy levels of the elliptic orbits. Though I cannot enter here upon the exact and rather tiresome proof of the foregoing statements, it may be interesting to describe in rough feature the solutions belonging to the second series of E levels. The solution may be performed in three-dimensional polar coordinates by assuming y to be a product of a function of the polar angles and a function of the radius r only. The former is a spherical surface harmonic whose order, increased by unity, corresponds to the azimuthal quantum number. The functions of r which come into play somewhat resemble, in rough feature, the Bessel functions, though with the difference that they have but a finite number of positive roots. And this number exactly corresponds to the radio quantum number. These roots lie within a region from the origin of about the same order of magnitude as the corresponding Bohr orbit. After having passed the last root with increasing 7 and a maximum or minimum not far away from it, the function tends to diminish exponentially as r approaches infinity. So the whole of the wave phenomenon, though mathematically spreading throughout all space, is essentially restricted to a small sphere of a few angstroms diameter, which may be called the atom according to undulatory mechanics. Any one of the above-mentioned solutions, consisting of a product of a spherical surface harmonic and a function of r only, greatly resembles a fundamental vibration of an elastic sphere with a finite number of 1 spheres, 2 cones, 3 planes as node surfaces. But it is surely not permissible to think that the wave motion constituting the atom is, in general, restricted to one of these solutions, the special selection and separation of which is very much influenced by the choice 6. It is, of course, not allowed to restrict the problem to 2 dimensions as in ordinary mechanics, since the wave phenomenon is essentially 3-dimensional. Undulatory dynamics 1059 of coordinates. To every one of the discrete values of E belongs a finite number of special solutions. In forming a linear aggregate of them with arbitrary constant multipliers, we get the most general solution of equation 18 for the particular value of Z. The number of arbitrary constants entering into this aggregate is exactly equal to what is called the statistical weight of this energy level, or, in other words, to the number of separate levels into which it is split up according to Bohr's theory and, by the way, also according to the present theory by the addition of perturbing forces that do away with the so-called degeneration of the problem. It will perhaps be remembered that in ordinary quantum theory, the number of states that is supplied by the method alluded to is not exactly correct. Definite experimental evidence compels us to exclude, by additional reasoning, more or less convincing from the theoretical point of view, a definite number of states, viz., those which have the equatorial quantum number 0. It is gratifying to be able to state that according to the present theory, the above-mentioned number of arbitrary constants, or, in other words, the number of separate levels or frequencies into which a degenerated E level is split up by a perturbing potential, is quite correct from the beginning. The theory needs no supplementation since it precludes a vibrational state corresponding to a Bohr orbit with equatorial quantum number 0. To complete this description, we may add that to the lowest E level, or from the wave motion point of view, its fundamental tone, which corresponds to the normal state of the atom, there belongs but one mode of vibration, and this is a very simple one. The function y shows complete spherical symmetry, and there are no node surfaces at all. Both the radial quantum number as well as the order of the spherical surface harmonic vanish. 5. I should like to discuss in a few words the question why equation 18 possesses finite solutions only for certain selected values of the constant E. The whole behavior described on the foregoing pages would be quite familiar to every physicist if the problem were a so-called boundary condition problem, i.e., if the function y were required only in the interior of a given surface, let us say a sphere of given radius, and had to fulfill certain conditions on the boundary of this sphere, e.g., to vanish. Now, though this is not the case, the problem is indeed equivalent to a boundary condition problem, the boundary being the infinite sphere. Thus, the selected values, 19, are quite properly to be named characteristic values, and the solutions that belong to them, characteristic functions of the problem connected with equation 18. The mathematical difficulty. 106. E. Schrodinger. Reason why no boundary conditions in the proper sense of the word are neither needed nor allowed at the infinite boundary is that a singular point of EQ18 is approached when we recede in any direction in space toward infinity. This can easily be seen by splitting up the equation in the way described above using polar coordinates. The resulting ordinary differential equation with the variable r has two singularities, at r equals 0 and at r equals infinity. It offers, for negative values of E, but one solution that remains finite at r equals 0, and but one that remains finite at r equals infinity. These two solutions are in general not identical, but they are for the selected values of E given by 19. But instead of dwelling on this purely mathematical side of the subject, I should like to present an idea why EQ18 shows such a queer behavior so as to make the matter clear to anyone who is acquainted only with the most general principles of wave theory. If E is negative, the bracket in EQ18 will be negative outside a certain sphere. Now, remembering the way in which EQ18 was derived from EQ15, we see that a negative value of the bracket in 18 clearly means a negative value of the square of wave velocity, or an imaginary value of wave velocity. What does this imply? The Laplacian operator is well known to be intimately connected with the average excess of the neighboring values over the value of the function at the point considered. Thus, the ordinary wave equation, 15, with a positive value of u, provides an accelerated increase or a retarded decrease of the function at all those points where its value is lower than the average of the neighboring values. And, vice versa, a retarded increase or an accelerated decrease at those points where the function exceeds the average of its neighborhood. Thus, the ordinary wave equation represents a certain tendency to smooth out again all differences between the values of the function at different points, though not at the very moment they appear and not indefinitely, as in the case of the equation for heat conduction. It will, however, certainly prevent the function from increasing or decreasing beyond all limit. If the quantity w squared, instead of being positive, is negative, which we have seen to be sometimes the case with EQ18, then all the foregoing reasoning is just reversed. There is in the course of time a tendency to exaggerate infinitely all humpies of the function, and even spontaneously to form humps out of quite insignificant traces. Evidently, a function which is subject to such a revolutionary sort of equation is continually 7 CEG R. Courant and D. Hilbert, Methoden der mathematischen Physik E, Berlin, Springer, 1924, Chap. 5, Section 9, page 1.
Undulatory dynamics 1061. Exposed to the very highest danger of increasing or decreasing beyond all limit. At any rate, it is no longer astonishing that special conditions must be fulfilled to prevent such an occurrence. The mathematical treatment shows that these conditions consist exactly in EZ having one of the second set of characteristic values given by 19, whereas the first set obviously prevents all accidents by making the square of the phase velocity positive throughout the space. 6. I will now give an account of some of the results that have hitherto been obtained with this new mechanics. Rather simple problems are offered by the harmonic oscillator and the rotator. The E levels of the former prove to be 2, 4 high, 2 equals 0, 1, 2, 3, and so on, instead of nonity according to the ordinary quantum theory. The E levels of the rotator are n plus 1 h squared divided by 8x squared t, the well-known n squared being replaced by 2, 1. If we are interested only in the differences of levels, as is actually the case, this amounts to the same as replacing 2 squared by n plus 4 squared. For n plus 4 squared minus n plus 1 equals 3, independent of n. It is well known that so-called half-quantum numbers are actually supported by the experimental evidence on most of the simple band spectra, and are probably contradicted by none of them. Mr. Foos, whose valuable help I owe to the Rockefeller Institution, International Education Board, has worked out the band theory of diatomic molecules in detail, taking into account the mutual influence of rotation and the fact that the latter is not of the simple harmonic type. The result is an exact agreement with the ordinary treatment, except that the quantum numbers become half-integer also in all correction terms. It would hardly have been possible to attack the problem just mentioned, as well as many similar ones, by direct methods, since the differential equation 16 is in general of a very difficult type. In many cases, however, this difficulty is overcome by the theory of perturbations which the writer has developed together with Mr. Foos. This theory, though much simpler, yet shows an interesting parallelism to the well-known theory of perturbations in ordinary mechanics. It allows the calculation by mere quadratures of the small modification of characteristic values and characteristic functions that are caused by 8E Fus on Physique 80-367-1926, another paper in press.
106. Schrodinger. Introducing an additional small term, function of the independent variables, in the coefficients of an equation whose characteristic values and characteristic functions are known. An interesting example of the application of this mathematical theory is afforded by the perturbation of the hydrogen atom caused by an external homogeneous electric field, Stark effect. The discrete Balmer levels, shown in EQ 19-2, are as characteristic values, not simple but manifold. Each of them corresponds to 6 characteristic values that coincide by chance, or, more properly speaking, because of the high symmetry or simplicity of the coefficients of EQ 18. The addition of an external electric field, small in comparison with the atomic field, does away with this symmetry and splits up every one of the Balmer levels into a set of near neighboring levels, though not into as many as n squared, because the splitting up in this case is not thorough. The writer has been able to show that these levels exactly coincide with those given by the well-known formula of Epstein, a rather severe test of our undulatory mechanics, since experimentally no deviation whatever, at least in the limit of a weak field, would have been allowed from this famous formula. But not only the levels, i.e. the frequencies, but also the intensities and polarizations of the emitted lines in the Stark effect can be calculated from undulatory mechanics in very fair agreement with experiment. Hitherto, we have not attached a definite physical meaning to the wave function y. It is possible, however, to give it a certain electrodynamical meaning, which will be discussed in detail in Section 8, and which converts our atom into a system of fluctuating charges spread out continuously in space and generating a resultant electric moment that changes with time with a superposition of frequencies, which exactly coincide with the differences of the vibration frequencies z-h, i.e., coincide with the frequencies of the emitted light. This in itself is highly satisfying. But in addition, it is possible to calculate the amplitudes of the harmonic components of the electric moment for any direction in space, e.g., in the case of the Stark effect, parallel to the electric field or perpendicular to the field. If the theory is correct, the squares of these amplitudes ought to be proportional to the intensities of the several line components, polarized in either direction. The rather laborious calculations have been performed, and the result is shown in Figure 1. In comparing theory with experiment, it must be borne in mind that the calculations have been performed only in the limit of a very weak external. 9. The experimental data were taken from I. Stark, Physics 48, 193, 1915. In these figures, theoretical intensities that are too small to be indicated by a line of the proper length are marked by a dot.
Undulatory dynamics. 1063. Field, and that in the region of field strength used in experiments, about 100,000 volts per cm, a very marked influence on the intensities is found, both by experiment and by theory. In particular, the very weak or vanishing components are enhanced with increasing field. The sum of the intensities of all the perpendicular components of one Balmer line turns out exactly equal to the sum of the parallel components of the same line. This is in full agreement with Stark's statement that no polarization of the emitted light as a whole is produced by the field. I ought to emphasize here that I was led to the foregoing nearly classical calculation of intensities by noticing posterior, i.e., after the main features of undulatory mechanics had been developed, its complete mathematical agreement with the theory of matrices put forward by Heisenberg, Born, and Jordan. The results shown in Fig. 1 may as well be called the results of the latter theory, though they have not yet been calculated by its direct application. The connection of the two theories is a rather intricate one and is by no means to be observed at first sight. 7.
It was stated in the beginning of this paper that in the present theory, both the laws of motion and the quantum conditions can be deduced from one Hamiltonian principle. To prove this, it must be shown that the wave equation, 16, can be derived from an integral variation principle. For this equation is indeed the only fundamental equation of the theory. In the case of a single material point moving in a conservative field of force, the only one considered in detail on the foregoing pages. The connection of EQ16 with the Hamiltonian principle is very simple and almost exactly the same as in ordinary vibration problems. Furthermore, this connection affords the simplest means of almost cogently extending the theory to a wholly arbitrary conservative system. Suppose the extreme values of the following integral extending over all space were required. Rim FFF SOV A squared plus F squared plus by squared plus V times dx dy dz. 20. All single-valued finite and continuously differentiable functions, y, being admitted to concurrence, that give the following normalizing integral a constant value, say 1. 1. 19. W. Heinsberg, Zeitz for PSY, 33, 879, 1925. M. Born and P. Jordan, M. 34, 858, 1925. M. Born, P. Jordan, and W. Heinsberg, Zeitz for PSY, 35, 557, 1926. M. Born, P. Jordan, and W. Heinsberg, Zeitz for PSY, 37, 263, 1926. 164. E. Schrodinger. 10. In carrying out the variation under this accessory condition in the well-known manner, equation 16 is found as the well-known necessary condition for an extreme value of 20, the constant, z being the Lagrangian multiplier with which the variation of the second integral has to be multiplied and added to the first so as to take care of the accessory condition. Thus, the normalized characteristic functions of equation 16 are exactly the so-called extremals of the integral, 20, under the normalizing condition, 21. Whereas the characteristic values, i.e., the values that are admissible for the constant z, are nothing else than the extreme values of integral. This property of the Lagrangian multiplier is well known and is easily recognized by observing that the non-conditioned extreme value of j can but be 0, any other value being capable as well of augmentation as of diminution by simply multiplying y by a constant. Now, the integrand of 20 proves on closer inspection to have a very simple relation to the ordinary Hamiltonian function of our mechanical problem, in the sense of ordinary mechanics. The said function is, cf. section 1, 1/2 m px squared plus py squared plus pz squared plus v x y z. 22. Take this function to be a homogeneous quadratic function of the momenta px, etc., and of unity, and replace therein px, py, pz, 1 by h ou by dx, h ou by dy, h ou by dz, y, respectively. There results the integrand of 20. This immediately suggests extending our variation problem and hereby our wave equation 16 to a wholly arbitrary conservative mechanical system. The Hamiltonian function of such will be of the form n ADLS sum am pi plus v 23 IWL KML with ADLK, the AI and V being some functions of the n generalized coordinates qi, etc. Take 23 to be a homogeneous quadratic function of px plus p, etc., 1, and replace these quantities by h ou by dq plus h ou by dqn y, respectively. Writing psi 4 for the determinant, d, dma, partial a by partial q, we form the integral h equals integral L dA psi p squared d AAN partial a by partial q partial a by partial as plus Vy squared plus AAN partial V by partial Q partial V by partial S dQi, etc. Undulatory dynamics 1065, taken over the whole space of coordinates and seek its extreme values, under the accessory condition Huff plus Vasterd ds dql equals 25. This leads to the generalization of EQ16, viz. At d seat Laudion plus SNT VE equals 0, 26. E being as before the Lagrangian multiplier of 25. The double sum appearing in 26 is a sort of generalized Laplacian in the n-dimensional, non-Euclidean space of coordinates. The necessary appearance of 4, 7 in an integral like 24 or 25 is well known from Gibbs statistical mechanics. A subscript n dqw plus d subscript dgy is simply the non-Euclidean element of volume, e.g., 7 sine theta d theta d phi dr, in the case of one material point of unit mass, whose position is fixed by three polar coordinates, r, theta, phi. In omitting the determinant, the integrals would not be invariant relative to point transformations. They would depend on the choice of generalized coordinates. It is EQ26 that has been used in all problems mentioned in section 6. 8. The question of the real physical meaning of the wave function y has been delayed. See section 6 until now for the sake of discussing it but once in full generality for a wholly arbitrary system. EQ16, or, in the more general case, EQ26 gives the dependence of the wave function on the coordinates only, the dependence on time being given for every one particular solution corresponding to a particular characteristic value h equals e, by the real part of xpin 2ekt 12h plus phi 1, I equals v1. Thus, parentheses. 6 being phase constants. So if UW, D equals 1, 2, 3 plus plus be the characteristic functions, the most general solution of the wave problem will be the real part of y equals CAUW XP REDW over H plus phi E, 27, equals. For simplicity's sake, we suppose the characteristic values to be all single and discrete. The CI are real constants. Now form the square of the absolute value of the complex function y. Denoting a conjugate complex value by a bar, this is WH equals 2 cross CI cross Artenia cosine 2REB parentheses EP by E minus ERT plus phi P minus phi R, 28. 106. E. Schrodinger. This, of course, like y, is in the general case a function of the generalized coordinates g plus gy and the time, not a function of ordinary space and time as in ordinary wave problems. This raises some difficulty in attaching a physical meaning to the wave function. In the case of the hydrogen atom, taken as a one-body problem, the difficulty disappears. In this case, it has been possible to compute fairly correct values for the intensities, e.g., of the Stark effect components, see section 6, fig 1, by the following hypothesis. The charge of the electron is not concentrated in a point, but is spread out through the whole space, proportional to the quantity p yp. Observed PHIVTEAP BAD TRLDETBADS Theoretical R1 Volte Ethos MTALI Fig 1. It has to be borne in mind that by this hypothesis, the charge is nevertheless restricted to a domain of, say, a few angstroms, the wave function W practically vanishing at greater distance from the nucleus, see section 4. The fluctuation of the charge will be governed by EQ 28, applied to the special case of the hydrogen atom. To find the radiation that by ordinary electrodynamics will originate from these fluctuating charges, we have simply to calculate the rectangular components of the total electrical moment by multiplying 28 by x, 9, 5 respectively, and integrating over the space, e.g. F yi wax d yitia equals 2dkk crev cos 2m ey minus evth plus delta yi dash phi my. 1. This procedure is legitimate only because and as long as the domain to which the charge is practically restricted remains small in comparison with the optical wavelength that corresponds to the frequencies ei minus ev-h. 2. In the sum vi, 1i', each pair of values of ja is to be taken but once, and the terms with j' equals ja are to be halved. Undulatory dynamics. 1067. 29. FF Smavasdayar. Thus, the total electric moment is seen to be a superposition of dipoles, which are associated with the pairs of characteristic functions which vibrate harmonically with the frequencies E, Z by H, well known from N. Bohr's famous frequency condition. The intensity of emitted radiation of a particular frequency is to be expected proportional to the square of CFF Sayuyidictex, Z. The supposition made on the C in calculating the intensities of the Stark effect components, Fig. 1, is that the C be equal for every set of characteristic values derived from one Balmer level, EQ 19-2, by the action of the electrical field. The relative intensities of the fine structure components will then be proportional to the square of the triple integral. This is found to be in fair agreement with experiment. The triple integral may be shown to be equal to what in Heisenberg's theory would be called the element of matrix Z, 1, 1. This constitutes the intimate connection between the two theories. But the important achievement of the present theory, imperfect as it may in many respects be, seems to me to be that by a definite localization of the charge in space and time, we are able from ordinary electrodynamics really to derive both the frequencies and the intensities and polarizations of the emitted light. All so-called selection principles automatically result from the vanishing of the triple integral in the particular case. Now, how are these conceptions to be generalized to the case of more than one, say of n electrons? Here, Heisenberg's formal theory has proved most valuable. It tells us, though less by physical reasoning than by its compact formal structure, that EQ 29, giving a rectangular component of total electric moment, has to be maintained with the only differences that 1. The integrals are 3n-fold instead of 3-fold, extending over the whole coordinate space. 2. Z has to be replaced by the sum del x, i.e., by the S component of the total electrical moment, which the point charge model would have in the configuration x1, y1, z1, x2, y2, z2, xn, yn, zn that relates to the element dx plus dy of the integration. But this amounts to making the following hypothesis as to the physical meaning of y, which of course reduces to our former hypothesis in the case of one electron only. The real continuous partition of the charge is a sort of mean of the continuous multitude of all possible configurations. 1068. E. Schrodinger. Of the corresponding point charge model, the mean being taken with the quantity yw as a sort of weight function in the configuration space. No very definite experimental results can be brought forward at present in favor of this generalized hypothesis, but some very general theoretical results on the quantity yw persuade me that the hypothesis is right. For example, the value of the integral of yi taken over the whole coordinate space proves absolutely constant, as it should if yw is a reasonable weight function, not only with a conservative but also with a non-conservative system. The treatment of the latter will be roughly sketched in the following section. 9. Equation 16 or more generally, 26, which is fundamental to all our reasoning, has been arrived at under the supposition that y depends on the time only through the factor A10 00 30. But this amounts to saying that P equals TUW by H, 31. From this equation and from equation 26, the quantity z may be eliminated, and so an equation be formed that must hold in any case, whatever be the dependence of the wave function y on time. APE equals 47Li dw dq dot SHR2V by H F40IH dw by dt equals 0. 32. The ambiguous sign of the last term presents no grave difficulty. Since physical meaning is attached to the product YW only, we may postulate for Y either of the two equations 32. Then W will satisfy the other, and their product will remain unaltered. Equation 32 lends itself to generalization to an arbitrary non-conservative system by simply supposing the potential function v to contain the time. Explicitly, a case of greatest interest is obtained by adding to the potential energy of a conservative system a small term, viz. The non-conservative potential energy produced in the system by an incident light wave. We cannot enter here into the details, but shall only present the main features of the solution. The effect of the incident light wave is that with each free vibration of the undisturbed system, frequency E by h, there are associated two forced vibrations with, in general, very small amplitudes, and with the two frequencies E D R R I by HA, V being the frequency of the incident beam of light. Following the same principles as in the foregoing section, we find every free vibration cooperating with Undulatory Dynamics 1069. Its associated forced vibrations to give rise to a forced light emission with the difference frequency FA/H times 2IU equals EY, i.e., with exactly the frequency of the incident beam of light. This forced emission is of course to be identified with the secondary wavelets that are necessary to account for absorption, dispersion, and scattering. In calculating their amplitudes, one finds them, indeed, to increase very markedly as soon as the incident frequency, V, approaches any one of the emission frequencies, EY minus EV/H. The final formula is almost identical with the well-known Helmholtz dispersion formula in the form presented by Kramers. The case of resonance cannot yet be treated quite satisfactorily, since a damping term seems to be missing in our fundamental equation, even in the case of a free conservative system. The radiation, which according to the assumptions of Section 8 is emitted by the cooperation of every pair of free vibrations, must of course in some way alter their amplitudes. This it does not do according to the assumptions hitherto made. But it is quite interesting to observe that also with that damping term still missing, we do not encounter the accident of infinite amplitudes in the case of resonance, well known from the classical treatment of the subject. The only thing that happens is that an incident light wave of ever so small an amplitude will raise the forced vibration of the system to a finite amplitude. And furthermore, if, for example, from the beginning only one free vibration was set up, say that belonging to EV, and if V equals KV minus K1, then the forced vibration raised to finite amplitude is in shape and frequency identical with the free vibration belonging to ZP. At the same time, the amplitude of the vibration Z is markedly diminished. The sum of squares of all amplitudes remains constant under all circumstances. This behavior seems to afford an insight, though incomplete, into the so-called transition from one stationary state to another, which hitherto has been wholly inaccessible to computation. 10. In the foregoing report, the undulatory theory of mechanics has been developed without reference to two very important things, viz. 1. The relativity modifications of classical mechanics, 2. The action of a magnetic field on the atom. This may be thought rather peculiar since L. de Broglie, whose fundamental researches gave origin to the present, 3 H. A. Kramer's Nature, May 10, 1924, Aug. 30, 1924, H. A. Kramer's and W. Heisenberg, Zates, F. PSI, 31, 681, 1925.
1070. E. Schrodinger. Theory. Even started from the relativistic theory of electronic motion, and from the beginning took into account a magnetic field as well as an electric one. It is of course possible to take the same starting point also for the present theory, and to carry it on fairly far in using relativistic mechanics instead of classical, and including the action of a magnetic field. Some very interesting results are obtained in this way on the wavelength, intensity, and polarization of the fine structure components and of the Zeeman components of the hydrogen atom. 4. There are two reasons why I did not think it very important to enter here into this form of the theory. First, it has until now not been possible to extend the relativistic theory to a system of more than one electron. But there is the region in which the solution of new problems is to be hoped from the new theory, problems that were inaccessible to the older theory. Second, the relativistic theory of the hydrogen atom is apparently incomplete. The results are in grave contradiction with experiment, since, in Sommerfeld's well-known formula for the displacement of the natural fine structure components, the so-called azimuthal quantum number, as well as the radial quantum number, turns out as half integer, i.e., half of an odd number, instead of integer. So, the fine structure turns out entirely wrong. The deficiency must be intimately connected with Uhlenbeck-Goldsmith's theory of the spinning electron. But in what way the electron spin has to be taken into account in the present theory is yet unknown. Zurich, Switzerland, September 3, 1926. W. V. Fock, Zeitz F. Physik 38, 242, 1926. G. E. Uhlenbeck and S. Goldsmith, Physia, 1925, Nature, Pell, 20, 1926.